first question when you start with generative AI and data science is fine tuning and why you should fine tune. So basically, fine tuning works like when when you're working with a large language model and you want to personalize it for your own data set. So this is the reason why customers or any entity start fine tuning. And another reason is that when LLM was invented or was created in 2022, 2023 with transformer architecture, what one limitation was that it hallucinates. So hallucination was the reason that fine tuning became very, very popular. And hallucination means that it start making up content. And so whenever you ask a question, it start making up content, and it might not be 100% accurate. So when customers started implementing LLM, this was a limitation they wanted to tackle because they want 100% correct answers if you are putting it in production. Even if you use ChatGPT today, if you are using it, you might have seen a message that ChatGPT responses are not 100% accurate. So all of this happens because of hallucination, and that is why it is important to fine tune the model based on your data set and domain, and personalize it based on your domain customization. You see is the fine tuning. So what does fine tuning means is that you can alter the model weights and parameters, and there are multiple techniques for fine tuning. So I'm going to cover all these 6 techniques and also tell you when to use what and what is the pros and cons between each and which is the most popular fine tuning technique. We'll start with pre-training and continued pre-training first, and then move to supervised fine tuning and parameter efficient fine tuning. And lastly, reinforcement learning with human feedback and model distillation. Okay, it's very, very important to know pre-training versus continued pre-training. Pre-training is basically you are creating a foundation model from scratch. Even with continued pre-training, you create a foundation model from scratch. So think like how was the GPT-2 created, or if you want to create your own transformer architecture and you have large data set, you can do pre-training and continue pre-training. So all the large language models which you see today, be it Quen, be it Llamas, be it Amazon Nova, all of these are built with pre-training. So let's understand what pre-training is and how it works. So basically you take an empty LLM with zero weights, and you pre-train it with unlabeled public data set. It is kind of a unsupervised learning. And then you try to create a domain adapted base LLM. So this domain adapted base LLM can be used for multiple tasks, like it can do generation, it can do question answering. So that is the whole process of pre-training. You see the cost here, which is interesting and important call out, that it is very, very costly to do pre-training because it takes large number of unsupervised data set. It can be a multimodal data set, it can be images, videos, audios, all type of data set you can imagine. And you pre-train a model, you need hardwares, and the training can run longer for like months. So that is how all the LLMs are getting created. Now, what is continued pre-training? So you already have a base model, right? You go to Hugging Face Hub and you can find those models, base model available. So you can download the model weights. I'm talking about open source model here. So basically, you take any open source model whose weights are available, and you can make the weights empty, and you perform continued pre-training. So the first step is generally unlabeled data set, and that gives you a base LLM. And then once you have a base LLM, you again train it with your private data set. So I worked with a customer who did continued pre-training for code generation use case. They wanted to do continued pre-training because they had proprietary code and they don't want to use any of the outside models. Proprietary data, when you have proprietary data, you have security concerns. So they went with continued pre-training and they took a model. I think they took an empty model like Quen, and they pre-trained it with the base LLM, and then they used the private data set to further fine tune it and domain adapt it. If you have any questions, you can always put it in the chat. Okay. Again, a quiz to break the silence. Which of these techniques does not change or alter model weight when it is customized?
Saurabh has answered C, RAG. Okay. Please make
One.
this a little bit more interactive. Tiago has said C, Priya has said C, RAG, Sanjay, RAG.
Okay. RAG is the correct answer. That is the correct answer. Okay. Thank you for following along and understanding the concepts till now. Now we are getting a little bit deeper. Supervised fine tuning versus parameter efficient fine tuning. So, if somebody asks you what is the most common fine tuning technique, it will be PEFT, or we call it PEFT in Gen AI world, so short for parameter efficient fine tuning. And why it is more popular than supervised fine tuning, we'll cover in this section. So, supervised fine tuning is basically full fine tuning. So, what does this mean is that you are taking a model parameters and updating all the model weights. So, for this, more data is needed. So then, what was the challenge here? Supervised fine tuning is great. The challenge is that you need a bigger hardware to. So if you take like a 8 billion model example, 8 billion model parameter example, and you're trying to change all the model weights. So if one parameter takes 2 byte, you will need at least 32 GB of RAM space, right? It's this big RAM you need just to fine tune, fit your model, and then fine tune it. So it will cost a lot, right? So that is why parameter efficient fine tuning was created. So this is considered as most cost effective fine tuning technique because the base model weights remain frozen and only few adapter modules are trained. So as a result, number of trainable parameters are significantly reduced and it gives you similar accuracy as SFT. And minimum of 10K samples are needed for parameter efficient fine tuning compared to supervised fine tuning. So this is the most popular fine tuning technique. You will see customers doing it every day. And even in PEFT, there are two further fine tuning techniques, which I'm going to cover in the next slide. Oh, okay. So yeah, we covered PEFT, where you freeze model weights while selectively training adapters or embedding layers. In that, there are two popular techniques. One is a LoRa or low rank adaptation, and then there is quantized LoRa. So LoRa, what does LoRa does is that it updates model weights via low rank matrix decomposition to adjust only subset of parameters. So suppose if you have like 8 GB model, your 8 billion model, and it is going to fit into 32 GB for full fine tuning. Same if you are going to do with LoRa, it will you can compress it to, so the rank determines how much compression you can do. So you can compress it to 1/16th of its size. So it will be around a few MBs. So the total size it takes to fine tune with LoRa with a GPU will be few MBs rather than the complete memory users. And then quantized LoRa is further quantization. So quantization means that you are compressing the model size or compressing the bits. So basically, if one word is represented by 8 bits, com- quantization means that same word will be represented by 1 bit. I'm just giving a random example, but the quantization can be 4 bit or 8 bit. So one word is represented by 32 bits in general. With quantization, you can reduce up to 4 bits. So basically, compressing the model size. So this will give you much more greater efficiency because you are compressing it further and less computational cost compared to low rank adaptation. Okay, last model distillation. So basically, model distillation is used when you have a big teacher model. So recently, Kimi K3 was launched, right? So it was supposed to be like, it is like 2.8 trillion parameters. It is the largest open source model. So what you can do, you can take a Kimi K3 model and distill a smaller student model with smaller size, which can be deployed in edge devices for inference. So model distillation is a technique where you take a big model and you create a small model out of it. And some of the use cases I see with distillation, customers like to take a bigger model and create a smaller model which can fit in small devices. So one of the customer was I was working with, they wanted to create those smaller models and put it on edge devices. So this technique was very, very powerful for that. And you do need a data set in this model distillation use case. Lastly, when to use which technique? Basically, I would recommend parameter efficient fine tuning, and LoRa and QLoRa is the most popular ones. And then model distillation. So use LoRa and QLoRa when fine tuning is needed with moderate resources. You don't have large data set and you don't want to spend a lot on fine tuning these models. And model distillation is used when deploying smaller models for inference while retaining teacher accuracy. Okay, again, quiz. Which of these fine tuning techniques use less data and compute for fine tuning? Pick two. Vishek, if you can read the answers if folks are writing.
Yes. So Tiago Lopez has answered Q, Laura, and model distillation. Saurabh has also said A and B, A and B. Okay.
Okay. I think LoRa and
And
QLoRa is the correct answer if you have been following along. Um, because LoRa and QLoRa is the technique which is very popular for fine tuning, and it uses very less because it doesn't change all the model weights. It freezes the weights and only fine tune the few parameters. Yeah. So that is why it is the most efficient technique. Last but not the least, preference alignment. Why we do need preference alignment? I'm not going into all these three techniques very deeply, but I want to roughly talk what is preference alignment. You took a model, you created a model from scratch, and then you did instruction tuning, and then you did fine tuning. Why do you need preference alignment? Basically, even if you have a fine-tuned model, you would still want to make it like human like answers. So if you go and see chat gpt, or if you have been using Nova, Gemini, whatever, you see like the plus sign, or whenever it asks for feedback, like plus sign, thumbs up sign, and thumbs down sign. So we are collecting, like these companies are collecting human label data, and based on that they are doing preference alignment with human like answers. So that is why it is very, very important to do preference alignment so that your answers are accurate and human like. So that is the last step of fine tuning. I will not say last step, but it will give you better accurate results if you do SFT plus preference alignment. So that's what we recommend customers, that you start with SFT and you do preference alignment with human label data set. It is also called RLHF, like human reinforcement learning with human feedback. So you might have heard this term. So that is the approach used here with preference alignment. So there are multiple techniques to do that. There is direct preference optimization, which is DPO, and then there's proximal policy optimization, which is same as used in RLHF techniques. And for if there are some AWS folks, they might know deep racer, which is deprecated now. So deep racer used to use the RLHF preference alignment technique, where it used to learn from um, the reward model how it is going to take the next move. So the PPO uses the same technique as the deep racer was, and group relative policy optimization is another technique. So we are not covering all these techniques, but it's always good to know that, okay, you might be thinking, oh, we have done fine tuning SFT, done. No, we are not done. It is a continuous process, and customers always come back with human label data set and make it much better. Okay, before I go into book review, I will take some questions.